Welcome, AXOR. Galactic Observatory tonight. The journey leads deep into one of the most extraordinary regions of the Milky Way, where Stephenson 2-18 shines as one of the largest stars ever discovered, hidden behind dense curtains of cosmic dust. This immense red hypergiant reveals a story of scale almost beyond imagination. From the way astronomers first detected it, to how they measured its astonishing size, to the unstable physics shaping its final years. This documentary explores the life of a star pushed to the very edge of what nature allows. It is a story of hidden light, immense power, and a future violent death that will scatter the building blocks of new worlds across the galaxy. If you enjoy calm, immersive space documentaries that help you relax while discovering the universe, please like this video, subscribe to AXOR Galactic Observatory, and join us for more quiet journeys through the cosmos. Along the inner band of the Milky Way, the sky grows thick with matter. Starlight gathers there in crowded streams, but much of it never arrives in clear form. Between Earth and the deep interior of the galaxy lie wide clouds of gas and dust, spread through the galactic plane like a dim veil. This is the flattened disk where many of the Milky Way's youngest and most massive stars are born, and it is also one of the hardest regions to study with ordinary visible light. Dust grains, though tiny, are abundant enough to change the map of the sky. They absorb and scatter shorter wavelengths more strongly than longer ones, weakening blue and green light first and letting more red light pass through. In visible photographs, this process creates dark lanes, broken patches, and false emptiness, as if whole regions of the galaxy contain fewer stars than they truly do. In reality, many of those apparently vacant directions are among the richest star fields in the Milky Way. They are not empty, they are hidden. This hidden quality shapes the search for extreme stars. The largest and brightest stars often live fast and die young, which means they remain close to the places where they form, inside dusty spiral arms and crowded stellar nurseries. The galaxy does not display them openly. It buries them behind intervening matter and leaves only a weakened, reddened signal to cross the long distance to Earth. In the constellation Scutum, close to the Milky Way's dense central regions, one such obscured area draws attention during systematic surveys of the sky. In the year 1990, astronomer Charles Bruce Stevenson identifies a massive star cluster in this difficult direction. The object later becomes known as Stephenson 2. At first glance, it is not a bright showpiece for small telescopes or a neat pattern visible to the eye. It is a concealed concentration of luminous stars embedded within one of the most crowded and dust-choked sightlines in the galaxy. Its discovery depends not on a clean window through space, but on learning how to look through a dirty one. That need changes the method of observation from the beginning. Visible light astronomy alone cannot reveal the full population of such a cluster, because too much of the incoming light is erased or distorted before it reaches the detector. A star that appears faint in ordinary wavelengths may in fact be extraordinarily luminous, its light simply dimmed by the material in between. To overcome this problem, astronomers turn to infrared astronomy. Infrared light has longer wavelengths than visible light, and those longer waves pass through dust more effectively. The dust does not vanish, but its obscuring power weakens enough for hidden stars to emerge. A region that looks broken and dark in visible images can become crowded and structured in infrared views. What seemed like absence becomes presence. What seemed like confusion begins to separate into individual sources. This change is not merely a technical improvement. It alters the census of the galaxy. It reveals stars, clusters, and star-forming environments that would otherwise remain underestimated or unknown. Stevenson 2 belongs to that concealed population. its existence becomes clearer because infrared surveys are able to pierce the dusty foreground and register the glow of cool, luminous stars inside the cluster. The logic behind this method is simple, though the practice is demanding. Dust grains are usually smaller than the wavelengths of infrared light used in many astronomical observations, so they interact less strongly with it. As a result, infrared detectors can receive radiation from stars that lie behind layers of obscuring material. Many massive evolved stars also emit strongly at infrared wavelengths, because their cool outer layers and surrounding dust re-radiate energy in that part of the spectrum. This makes infrared observations especially useful in crowded, dusty regions of the Milky Way, where old assumptions based on visible brightness alone can be misleading. Over time, a series of observatories strengthens this hidden view of the galaxy. The infrared astronomical satellite opens an early space-based window onto the infrared sky and helps identify many dusty and luminous sources. Later, the 2-micron all-sky survey maps the sky in near-infrared wavelengths with far greater detail, giving astronomers positions and brightness measurements for stars that are difficult or impossible to study in ordinary light. Space missions such as Spitzer extend the reach of infrared astronomy further, offering sharper sensitivity and access to longer wavelengths that probe cooler dust and deeper obscuration. Ground-based facilities also contribute, especially from dry, high-altitude sites, where the atmosphere interferes less with incoming infrared radiation. Together, these tools transform the Milky Way from a partially blinded view into a layered structure whose hidden populations can be studied with increasing confidence. In the direction of Stephenson 2, this matters profoundly. The cluster sits far from Earth, at a distance of roughly 20,000 light-years, though exact values vary among studies and remain subject to refinement. Across that span, light must cross not empty perfection, but a long and contaminated path through the galactic disk. Every cloud along the way modifies the signal. Infrared techniques do not remove all uncertainty, but they reduce the blindness enough to allow a meaningful picture to form. Astronomers can begin distinguishing which stars truly belong to the cluster, how bright they are, and what kind of stellar environment surrounds them. A cluster like this is important because it gathers many massive stars in one place, and therefore acts as a natural laboratory for stellar evolution under extreme conditions. Yet before any of that can be understood, the cluster first has to be found in reliable form. Discovery, in this case, is not a moment of simple seeing. It is the gradual correction of a false visual impression created by dust. The dusty plain of the Milky Way teaches the same lesson again and again. The galaxy is richer than it looks, and the apparent darkness of many regions is often the mark of obstruction rather than emptiness. Stevenson too emerges from that lesson. It is discovered not because the sky and scutum becomes transparent, but because astronomy learns how to read light that survives the passage through obscuring matter. The cluster remains embedded in one of the most difficult regions of the galaxy to observe, and that difficulty is part of its meaning. It reminds observers that the outer appearance of the Milky Way is shaped as much by what blocks light as by what emits it. In that concealed band of stars, gas, and dust, infrared astronomy changes hidden structure into visible evidence, and from that evidence a buried stellar city begins to take shape. Within the concealed population of Stephenson 2, one star begins to separate itself from the rest through the strength of its infrared signal. The cluster already contains many red supergiants, each one a massive star in a late stage of life, swollen to enormous dimensions and glowing with a cool reddish colour. Even among such extreme neighbours, however, one object stands out. That star becomes known as Stephenson 2-18. Its distinction does not begin with a dramatic visible image, because the same dust that hides the cluster also weakens the direct visual impression of every member within it. Instead, its exceptional nature emerges through careful comparison of measured brightness, infrared color, cluster membership, and spectral character. In a field crowded with evolved massive stars, Stevenson 2-18 appears unusually luminous, and this unusual brightness draws sustained attention. The process is gradual. Astronomers do not identify a record-breaking star from a single glance or a single number. They notice that one source among the cluster's red supergiants seems brighter than expected for an ordinary member of such a group. They compare it against nearby stars observed in the same region, using infrared surveys that reduce the effect of dust and preserve more of the star's true energy output. The star does not announce its scale directly. It first appears as a signal that remains prominent even after the known difficulties of distance, reddening, and crowding are taken into account. In that sense, Stevenson 2-18 enters astronomy first as an anomaly within a rare population. The rarity of the surrounding population matters. Red supergiants are not common stars. They represent a brief and unstable phase in the evolution of massive stars, one that occurs after core hydrogen burning has ended and the outer envelope has expanded to immense size. In many parts of the galaxy, only a handful may be found in relative isolation. Stevenson 2, by contrast, contains an unusually rich concentration of them, which immediately makes the cluster important. A massive cluster with many red supergiants offers an unusually controlled setting, because its stars are broadly similar in age and lie at roughly the same distance. This reduces some of the uncertainty that affects the study of isolated stars. If many stars are born together, then differences among them can be interpreted against a shared background. Within this common setting, Stevenson 2-18 is not merely bright in an absolute sense, it is bright relative to its already remarkable companions. That is why it attracts close study. The first task is to determine whether the star truly belongs to the cluster or merely lies by chance in the same direction. In a crowded line of sight through the Milky Way, overlap can be deceptive. A foreground star may appear close to a distant cluster, and a background star may seem embedded within it. Astronomers therefore look for signs of shared membership, including consistent radial velocity, similar reddening, and a position compatible with the cluster's structure. Stevenson 2-18 proves to be associated with the cluster rather than an unrelated intruder. This is essential. If it shares the cluster's distance, then its great apparent brightness becomes evidence for extraordinary intrinsic luminosity rather than mere proximity. Once that link is established with reasonable confidence, the star's importance grows rapidly. Infrared photometry becomes one of the key tools in this stage. By measuring the star's brightness in multiple infrared bands, astronomers can estimate how much dust lies along the line of sight and how red the object appears after that dust has altered the signal. This matters because the observed color of a distant red supergiant combines two effects. The star is truly cool, and the intervening dust makes it appear even redder. Untangling these influences is necessary before its physical nature can be judged. Stevenson 2-18 remains impressive even after these corrections are considered. Its observed infrared prominence is too strong to dismiss as a simple artifact of dust or chance. It becomes clear that the star is one of the most luminous red supergiant candidates known. Its brightness alone does not yet give its full size, but it establishes the first solid reason to think the star may be extraordinary on a galactic scale. Another clue comes from the cluster itself. In a young massive cluster, the most evolved stars offer a record of the upper end of the initial stellar population. When many red supergiants are present together, they indicate a particular age range in which very massive stars have already left the main sequence, but have not yet ended in explosion. Stevenson 2 is one of the richest known examples of this phase. The presence of so many red supergiants suggests that the cluster formed a substantial number of high-mass stars, and Stevenson 2-18 appears to sit near the most extreme edge of that evolved group. It is not simply another red star in a dusty field. It is one of the cluster's dominant evolved members, a beacon within a population already defined by stellar excess. This is why astronomers begin to regard it not just as interesting, but as potentially record-setting. Even at this stage, caution remains important. Brightness can mislead if distance is wrong, if dust corrections are incomplete, or if the source is blended with unresolved nearby stars. A dense cluster increases the chance of confusion, especially in observations with limited angular resolution. Astronomers therefore rely on repeated observations, improved catalogue data, and spectroscopy to confirm that the signal belongs to a single cool supergiant rather than a composite effect. Stevenson 2-18 continues to withstand that scrutiny. The star remains luminous, cool, and cluster-associated. Its prominence survives the standard test that would reduce many apparent anomalies to ordinary explanations. By this point, the picture has changed. The star is no longer just a bright infrared source in a hidden cluster. It has become a leading candidate for one of the largest known stars, though that conclusion still depends on further measurement and interpretation. The importance of this stage lies in restraint, before size, before spectacle, before comparisons with the solar system. There is the quieter scientific step of noticing that one source in a difficult field refuses to fit within ordinary expectations. Stevenson 2-18 earns attention in precisely that way. Its signal persists above the background of crowding, dust, and uncertainty. In a cluster famous for red supergiants, it still appears exceptional. That exception is the beginning of its rise from obscurity. Long before the star becomes widely described as a colossal hypergiant, it first exists in the data as a persistent excess of light, a cool luminous presence that demands explanation. From that demand, the deeper investigation begins. Once Stevenson 2-18 is recognized as an exceptional member of its cluster, the next problem becomes one of scale. The star is far away, deeply reddened by dust, and visible only through the long filtering path of the inner Milky Way. Under such conditions, size cannot be measured directly in the simple visual sense. No telescope resolves its broad disk as a clear globe in the sky. Instead, astronomers must reconstruct its physical nature from the small amount of information that survives the journey to Earth. The essential challenge is to turn a faint and altered signal into a description of a real star with real dimensions. That reconstruction begins with apparent brightness, the amount of light received at Earth. But apparent brightness alone says almost nothing without distance. A nearby candle can outshine a distant fire, and a modest star close to Earth can appear brighter than a vastly more powerful star across the galaxy. For Stevenson 2-18, this distinction is decisive. Its observed light reaches Earth only after travelling roughly 20,000 light-years, with exact estimates differing from one study to another. That enormous distance means even a highly luminous star can appear modest in the detector. If a star still looks conspicuous under those conditions, then its true power may be extraordinary. The first step, therefore, is not merely to note that the star is bright, but to connect its brightness to a credible distance. Here the cluster becomes invaluable. An isolated star in a dusty region of the Milky Way is difficult to place. A star inside a cluster can be studied through the shared properties of the group. Astronomers estimate the distance to Stevenson 2 by examining its stellar population, the brightness distribution of its members, their motions, and their relation to structures in the galactic plane. the process is not perfectly settled, because distance measurements in such obscured regions remain difficult. But the cluster provides a framework strong enough to narrow the possibilities. Once Stevenson 2-18 is accepted as a cluster member, it inherits the cluster's estimated distance rather than floating in uncertainty as an isolated source. That connection transforms the interpretation of its light. A star that would seem merely interesting at a few thousand light years becomes astonishing at many times that range. Dust correction is the next step. The starlight that reaches Earth is not the same light that leaves the star. Intervening dust absorbs and scatters part of the signal, especially at shorter wavelengths, making the star appear dimmer and redder than it truly is. Astronomers account for this by estimating the extinction, which is the loss of light caused by material along the line of sight. They use the star's colours, compare them with expected values for similar stars, and analyse the broader properties of the cluster to estimate how much of the original light has been removed. This is never exact in a region as complicated as the inner Milky Way, because dust is clumpy and uneven, but the corrections bring the observations closer to the star's intrinsic output. Once apparent brightness is corrected for distance and extinction, astronomers can estimate luminosity, the total energy the star emits. Luminosity is the true scale of a star's radiative power. It is not what the eye sees from Earth, but what the star is actually producing. For a cool evolved star like Stevenson 2-18, much of that energy emerges at red and infrared wavelengths, so measurements must account for the full spread of its radiation rather than one narrow band. This is why astronomers use bolometric estimates, which aim to capture the star's total energy output across all wavelengths. The final number depends on the adopted distance, the extinction model, and the spectral classification, which means uncertainty remains built into the result. Yet even allowing for those uncertainties, the luminosity inferred for Stevenson 2-18 is immense. At this stage, the star is no longer just a bright point in a catalogue. It has become an object whose power rivals the most luminous cool stars known. Still, luminosity alone does not yield radius. A small hot star and a huge cool star can emit similar total energy if the balance between temperature and surface area differs. What distinguishes Stevenson 2-18 is that it appears to be relatively cool while also being extraordinarily luminous. That combination is the key. A cool surface emits less energy per unit area than a hot one. So if a star is cool, yet still radiates enormous total power, it must compensate with a vast emitting surface. In other words, it must be physically enormous. Before that conclusion can be drawn, however, temperature must be estimated with care. This is done through spectral analysis and comparison with other red supergiants, allowing astronomers to assign an approximate effective temperature. The value is much lower than that of the Sun, consistent with a deeply expanded outer envelope. Once luminosity and temperature are both in hand, the star can be placed on the Hertzsprung-Russell diagram, the great map of stellar evolution that compares brightness and temperature. On that diagram, Stevenson 2-18 occupies the cool and luminous upper region where red supergiants and hypergiants reside. Its location is already a clue to extraordinary size. The diagram does not directly show the star's radius, but it shows the relationship between the two ingredients from which radius can be inferred. The star's place there tells astronomers that they are dealing not with a compact luminous object, but with a swollen outer structure extended over an immense volume. Another source of confidence comes from comparison within the cluster. Because Stevenson 2 contains many red supergiants, astronomers can compare Stevenson 2-18 to stars that share roughly the same age and environment. It still appears to sit near the extreme upper end of the cluster's evolved population. That relative standing helps reduce the likelihood that the star's prominence is a result of unusual foreground placement or some isolated mistake in interpretation. It is exceptional not only by theoretical reconstruction, but also within its own stellar family. Yet the uncertainty never entirely disappears. Distance estimates to distant obscured clusters can shift as methods improve. Extinction corrections can change with better dust models. Spectral classifications can be refined. Because of this, every physical estimate for Stevenson 2-18 carries ranges rather than perfect certainty. That caution is part of the science, not a weakness in it. Astronomers do not claim more precision than the data can support. What they can say is that the star is far away, intrinsically brilliant, very cool by stellar standards, and therefore an outstanding candidate for one of the largest stars ever identified, from a faint reddened signal hidden in the galactic plane. A physical picture begins to emerge, not a modest star magnified by circumstance, but a distant giant whose true scale survives the long journey of ancient light. The light of Stevenson 2-18 carries more than brightness. Once the star's distance and corrected luminosity begin to take shape, astronomers turn to its spectrum, because a spectrum reveals the physical condition of a star more clearly than brightness alone ever can. A spectrum is the spread of starlight into its component wavelengths, a record of how matter in and around the star absorbs and emits radiation. To the eye, a red supergiant may simply look warm in colour, but under spectral analysis that broad redness separates into a structured pattern of lines and bands. Those patterns allow astronomers to infer temperature, composition, atmospheric structure, motion, and sometimes the presence of matter flowing away from the star. In a case like Stevenson 2-18, where direct imaging cannot show the full physical form of the object, spectroscopy becomes one of the central paths from signal to reality. The first broad conclusion from the spectrum is that the star is cool by stellar standards. Cool in this context does not mean cold in any ordinary sense. The surface remains thousands of degrees above the boiling point of any familiar substance on Earth. Yet compared with the Sun, and especially compared with hot blue massive stars, the outer layers of Stevenson 2-18 are relatively cool. This lower temperature shifts the peak of its radiation toward longer wavelengths, and allows molecules to exist in parts of the atmosphere that would be destroyed in hotter stars. These molecules leave signatures in the spectrum, particularly in the form of broad absorption bands. Among the most important are bands produced by titanium oxide, a molecule that appears prominently in cool stellar atmospheres. Such features are characteristic of late-type stars and help astronomers place the star within the family of red supergiants. The spectrum does not merely say that the star looks red, it explains why. Classification follows from this evidence. By comparing the observed spectral features of Stevenson 2-18 with standard stars whose types are already established, astronomers determine that it belongs to the late spectral classes associated with very cool luminous supergiants. The precise subtype can vary slightly between studies depending on the quality of the observation, the wavelength range used, and the changing appearance of the star over time, because extreme supergiants are often variable. Even so, the broader conclusion remains stable. This is a red supergiant or red hypergiant, a star with a cool extended atmosphere and enormous luminosity. That classification matters because it narrows the plausible range of effective temperature. It also places the star in a brief and unstable evolutionary state near the end of a massive life. Spectroscopy also helps distinguish intrinsic stellar properties from the effects of the foreground dust. Dust can redden the overall colour of the star, but it does not create the specific molecular and atomic patterns that define a cool stellar atmosphere. In that way, the spectrum acts as a corrective to appearances. A star might look red either because it is cool or because dust has dimmed its blue light. but a spectrum can separate those possibilities. For Stevenson, 2-18, the absorption features support the conclusion that the star is truly cool, not merely reddened by the interstellar medium. This is a crucial point. Without it, the star might still be interpreted as a more compact object, whose colour is largely an artifact of obscuration. The spectrum shows instead that the star's outer layers really do occupy the thermal regime of an extreme red supergiant. Atomic lines add another layer of information. Features associated with elements such as calcium, iron, and other metals help astronomers judge surface gravity and luminosity class. In giant and supergiant stars, the low density and low surface gravity of the outer atmosphere affect how these lines appear. The atmosphere is more rarefied than that of a smaller star. And this changes the balance of pressure, broadening, and line strength. In luminous, cool supergiants, certain features become especially prominent or take on shapes consistent with a swollen atmosphere. Stevenson 2-18 shows this general pattern. Its spectrum supports not only cool temperature, but also the low surface gravity expected for a star whose outer layers have expanded across an immense distance from the centre. This is one of the ways spectroscopy points indirectly toward vast size even before formal radius calculations are made. The spectrum can also hint at motion in the atmosphere. Massive evolved stars do not possess quiet surfaces. Their outer layers pulse, convect, and shed matter in winds that may be dense, clumpy, and asymmetric. In some red supergiants, these motions produce shifts or asymmetries in spectral lines. The signal from Stevenson 2-18 is not always simple, and part of that complexity may reflect the restless nature of its atmosphere. Some observations suggest behavior consistent with strong mass loss, a common property of the most luminous, cool, evolved stars. Material lifted away from the surface can cool and form dust farther out, contributing additional infrared emission. This does not mean the star is surrounded by a neat shell in perfect symmetry. More likely, the environment is uneven, shaped by slow outflow, large convective cells, and episodic loss of matter. Spectroscopy does not provide a full picture of that structure by itself, but it shows that the star is not a static sphere. It is an active atmosphere in motion. Composition is another area where the spectrum informs the interpretation. The outer layers of an evolved massive star may contain the chemical traces of deep internal processing brought upward through convection and mixing. In many red supergiants, the surface abundances differ from those of less evolved stars because nuclear processed material from the interior has partially reached the atmosphere. Detecting these changes in detail can be difficult at great distance and through heavy extinction, but the general expectation fits the evolutionary status of Stevenson 2-18. The spectrum belongs to a star that has already passed through earlier stages of hydrogen burning, and whose outer appearance reflects prolonged internal change. In that sense, the atmosphere becomes a record not just of present condition, but of past evolution. All of this matters because the spectrum anchors the star's physical interpretation. Brightness suggests importance, but the spectrum identifies the nature of the source that is producing that brightness. It tells astronomers that Stevenson 2-18 is not a hot compact star, not a foreground intruder, and not simply a dust-reddened ambiguity. It is a genuinely cool, enormously luminous, evolved, massive star with an extended low-gravity atmosphere. That combination is rare, and it sets up the next inference with increasing force. A star this cool cannot radiate such enormous power unless its emitting surface is extraordinarily large. The spectrum, therefore, does more than classify. It closes off many ordinary explanations and strengthens one extraordinary conclusion. The red character of Stevenson 2-18 is real. Its cool outer layers are real. its swollen atmospheric structure is real. From that spectral evidence, the giant begins to acquire a more definite physical form, with distance, luminosity, and temperature in place. The scale of Stephenson 2-18 can be translated from inference into physical size. The logic is one of the most elegant in stellar physics. A star radiates energy from its surface, and the total energy it emits depends on two things taken together: how hot that surface is and how much surface area it has. A very hot star can shine intensely even if it is not especially large, because each part of its surface emits a great deal of energy. A cooler star emits less energy from each equal patch of surface. If such a cooler star is still extraordinarily luminous overall, then it must make up for its lower surface output by having far more emitting area. For Stephenson 2-18, this is the decisive combination. It appears to be a cool, evolved, massive star, yet its luminosity is immense. The unavoidable implication is that the star's radius must be vast. This conclusion is usually expressed through the Stefan-Boltzmann law, which relates luminosity, radius, and effective temperature. Astronomers do not need to see the disk of the star directly in order to apply it. Once they estimate total energy output and surface temperature, the radius follows. The calculation is conceptually straightforward, though every input carries uncertainty. Distance affects luminosity. Dust correction affects the recovered energy output. Spectral classification affects the adopted temperature. Change any of these and the estimated radius changes as well. That is why published values for the size of Stephenson 2-18 differ somewhat from one study to another. Even so, across those variations the result remains astonishing. The star's radius is commonly estimated at around 2,000 solar radii, with some analyses placing it somewhat below or somewhat above that figure depending on assumptions. Whatever exact value is favoured, the conclusion does not change in character. This is a star whose outer layers extend across a volume almost beyond ordinary intuition. The comparison with the Sun is especially striking. The Sun is an ordinary main-sequence star, hot enough at its surface to produce a yellow-white glow and stable enough to maintain a relatively compact form for billions of years. Stephenson 2-18 is very different. Its surface is much cooler, but its total radiative output is vastly greater because its envelope has expanded to extraordinary dimensions. If the Sun were inflated to the radius estimated for Stephenson 2-18, while somehow keeping the same central location in the solar system, the familiar scale of the planetary orbits would be transformed into an internal map of the star. Mercury and Venus would vanish deep inside the atmosphere. Earth would be engulfed. Mars would also lie within the swollen envelope. Even Jupiter, so distant on the scale of the inner planets, would no longer orbit in open space. The photosphere, which is the visible surface from which most of the star's light escapes, would extend beyond the orbit of Jupiter and approach, or even past the orbit of Saturn, depending on the adopted radius. This comparison is often used because it translates an abstract number into something that can be mentally pictured. Yet even that image remains incomplete. A red hypergiant does not have an edge as crisp as a solid sphere. Its outer layers are diffuse, extended, and in motion, so the meaning of radius itself is less sharp than it is for a small stable star. In a star like Stephenson 2-18, the visible surface is not a rigid shell. It is a region defined by whether gas becomes opaque enough for light to emerge. That region can shift somewhat with wavelength, with pulsation, and with the details of the atmosphere. This is one reason why the radius estimate is not a single perfectly fixed number. The star is not a neat ball with a hard boundary. It is a swollen atmosphere whose observed surface depends on how and where it is measured. Even with that caution, the physical immensity remains secure. One way to appreciate the scale is to consider surface area rather than radius alone. Surface area increases with the square of the radius. So a star with roughly 2,000 times the Sun's radius has millions of times the Sun's surface area. That enormous area compensates for the lower energy emitted by each unit of surface at a cooler temperature. The star shines not because each square region is unusually intense, but because there are so many such regions spread across a gigantic envelope. This helps explain how a cool red star can rival or exceed the luminosity of much hotter stars. Size becomes a substitute for temperature. Another comparison involves light travel time across the star. In ordinary experience, the dimensions of objects are so small that light seems instantaneous. For a star like Stevenson, 2-18, light itself requires hours to cross the diameter. This is not a decorative fact. It shows that the star's atmosphere is so extended that physical changes in one region are not immediately reflected everywhere else. The outer layers do not behave like a tightly coupled body. They are vast enough for convection, pulsation, and radiation to interact across long distances and timescales. The star is large not only in the geometric sense, but in the dynamical sense as well. Processes within it unfold across an enormous physical stage. Yet the calculation of radius must always be kept tied to its assumptions. The effective temperature of a red hypergiant is not as easy to determine as the temperature of a compact star with a simpler atmosphere. Molecules, dust, and extended outer layers complicate the spectrum. The luminosity depends sensitively on the adopted distance to Stevenson 2, and on how extinction is corrected across the line of sight. Because of this, astronomers treat the largest published radius values with caution. The star may be one of the largest known, perhaps the largest known by some estimates. But the ranking is not beyond revision. What matters more than the exact placement in a record book is the physical class it occupies. Stevenson 2-18 belongs among the most extreme swollen stars yet identified, at the edge where late stellar evolution produces objects of staggering radius and unstable structure. The calculation also reveals something subtle about what it means for a star to become gigantic. Radius is not a direct measure of mass. A star can have an enormous radius while containing only a limited amount of material in its outer layers, provided that material is spread thinly across a huge volume. In the case of Stevenson 2-18, the immense radius signals dramatic expansion, not an equally dramatic increase in mass. The star has not become gigantic by adding matter. It has become gigantic by redistributing its outer envelope into a far more extended form. That distinction becomes crucial for understanding how such a vast object can still obey the laws of stellar structure. For now, the essential point is this from the measured combination of cool temperature and extraordinary luminosity. The mathematics leads to a star of almost incomprehensible size. Stevenson 2-18 is not merely bright, not merely red, not merely distant. It is physically immense on a scale that pushes the solar system from a system of planets into a measuring stick. Once the radius of Stevenson 2-18 is expressed in solar units, the imagination immediately reaches for the solar system, because planetary orbits provide one of the few familiar scales large enough to make such a number meaningful. A radius of around 2,000 times that of the Sun is not just a larger star in the ordinary sense. It is a star so expanded that the architecture of the inner solar system would fit inside it with room to spare. If Stevenson 2-18 were placed where the Sun now sits, the order of the planets would remain the same, but their relation to the central star would be transformed from orbiting bodies into embedded markers inside a giant atmosphere. Mercury would be lost first, not merely scorched but entirely submerged within the stellar envelope. Venus would share the same fate. Earth, which circles the Sun at a distance that defines the ordinary scale of human thought about the cosmos, would not come close to safety. Its orbit would also lie deep within the star. Mars, which already feels remote when compared with Earth, would still be swallowed. Even the great belt of small rocky bodies between Mars and Jupiter would have no open space left to inhabit. The point of this comparison is not spectacle alone. It reveals how far stellar evolution can carry a massive star away from the compact dimensions of its youth. The Sun appears large to human eyes and dominates the solar system by mass and light. Yet on the scale of evolved hypergiants, it is physically modest. Stevenson 2-18 illustrates how a star can begin as a concentrated body and end with its outer layers distributed over distances that rival the planetary structure of an entire system. In such a comparison, Jupiter becomes the next great marker. Jupiter orbits far beyond the terrestrial planets and contains most of the planetary mass in the solar system, so it often serves as a natural boundary between the familiar inner region and the deeper outer domain. For a star like Stephenson 2-18, even this boundary no longer means safety. Many radius estimates place the visible surface beyond Jupiter's orbit. Some place it near Saturn's orbit. That means the star's photosphere, the layer from which most visible light escapes, would extend across a region that in the solar system includes not only rocky worlds, but also the giant planet that usually signifies enormous distance from the Sun. This is why the star's size is so difficult to grasp. Human intuition is formed from terrestrial objects, then stretched a little to planetary scales, and only with effort extended to astronomical distances. Stevenson 2-18 compresses several of those mental scales together. It makes Jupiter seem local. Saturn becomes a plausible boundary marker for the stellar surface. Yet even that picture needs care. When astronomers say the star would reach to Saturn or beyond Jupiter, they are referring to the approximate location of the effective visible surface. A red hypergiant does not end abruptly at that line. Its atmosphere thins gradually outward, and matter may continue much farther in the form of winds, clumps, and circumstellar dust. In one sense, then, the comparison with planetary orbits understates the full spatial influence of the star. The formal radius describes the place where the atmosphere becomes optically thick enough to define a photosphere, but the surrounding material can extend well beyond that. The star is not a polished globe nested cleanly inside the solar system model. It is more like a central furnace wrapped in an enormous, diluted, moving envelope whose influence fades outward rather than stopping sharply. This subtlety matters because it helps prevent a misleading picture of the star as something dense and solid across its whole extent. If Earth or Jupiter lay inside such a star, they would not be moving through a compact wall of matter. They would exist, for as long as they could survive at all, within deep layers of hot gas whose density changes with radius. Of course, no ordinary planet would remain intact under such conditions. Temperatures, radiation, drag, and tidal effects would destroy the familiar structure of planets long before any stable orbit could continue. But the physical meaning of being inside the star is different from being buried inside a solid object. The atmosphere of a hypergiant is vast precisely because its outer layers are so diffuse. That is why planetary orbit comparisons are so effective, and yet also incomplete. They communicate distance well, but they do not by themselves communicate density, structure, or instability. Saturn provides one of the most dramatic reference points because it lies far enough from the Sun that ordinary language treats it as part of the outer solar system, a realm of broad, cold distances. To say that a star may approach or exceed that orbit is to say that the star's visible surface spans a region that human culture often imagines as already immense. Yet even Saturn is not the end of the solar system. Beyond it lie Uranus, Neptune, the Kuiper belt, and the distant comet reservoirs that extend the Sun's gravitational influence far into interstellar space. Stevenson 2-18 does not reach those outermost regions with its photosphere, but by the time one is comparing a stellar surface to Saturn, the meaning is already clear. This is no ordinary giant. It occupies a size regime where the vocabulary of planets becomes necessary to keep the scale intelligible. There is another reason the solar system comparison is scientifically useful. Planetary orbits are measured and stable enough to provide a common mental ruler across cultures and eras. When astronomers describe Stephenson 2-18 in solar radii, the figure is exact in one technical sense but emotionally abstract. When they say the star would engulf Earth and stretch toward Jupiter or Saturn, they are converting an expert unit into a spatial image that preserves the same physics. The comparison does not replace the measurement, it translates it. It also emphasizes that the most extreme stars are not simply a little larger than ordinary ones. They belong to a different domain of structure entirely, where the distance from center to surface becomes comparable to the scale of planetary systems. This translation from number to image has consequences for how the star is understood. It makes clear that Stephenson 2-18 cannot be thought of as a scaled-up sun with the same neat layered compactness. A star whose surface reaches across the orbits of multiple planets must have an atmosphere governed by slow gravity, low density, and persistent instability in its outer layers. Its size alone implies fragility. The very fact that the star can be mapped against the solar system suggests that its outer envelope has become extended to a point where ordinary intuitions about stars begin to fail. The planetary comparison, therefore, does more than dramatize the measurement. It reveals the kind of object Stephenson 2-18 has become a late-stage stellar giant, so expanded that the familiar map of the Sun's domain turns into an internal diagram of its fading outer form. The immense radius of Stephenson 2-18 can easily create the false impression that the star must also contain an equally overwhelming amount of matter, packed throughout its full volume. Ordinary experience encourages that assumption. Large objects on Earth usually owe their size to having more material, greater density, or both. In stars, however, the relation between size and substance becomes more subtle, especially in the final stages of massive stellar evolution. A red hypergiant reaches extraordinary dimensions not because every part of it becomes thick and compact, but because its outer layers expand outward and become remarkably diffuse. The star is enormous in extent, yet much of that extent is occupied by gas at very low density compared with the dense regions deep inside. This distinction is crucial for understanding how a star can swell to a size that rivals planetary orbits, while still remaining within the bounds set by stellar physics. The center of the star is not gigantic in the same way as the whole object appears gigantic. Most of the mass remains concentrated toward the interior, where gravity is strongest and matter is compressed to far greater densities. Surrounding this deeper core is an extended envelope of hot gas whose density drops rapidly with increasing distance from the center. By the time one reaches the outer regions that define the visible surface, the material has become thin enough that the star's atmosphere resembles a vast, rarefied shell rather than a dense body. This is why it is possible for the radius to become almost unimaginable, while the total mass remains only a modest multiple of the Sun's mass. Massive, yes, but not massive in proportion to the gigantic volume enclosed by the visible surface. If the star's material were spread with anything like uniform density from center to edge, the total mass would be far greater than observations and stellar evolution allow. The swollen nature of the outer envelope solves that apparent contradiction. One way to understand this is through average density. Although average density can be a misleading simplification for a star with strong internal gradients, it still reveals the scale of the effect. When a relatively limited amount of matter is distributed across an enormous sphere, the average density becomes extremely low. For a hypergiant such as Stevenson 2-18, that average density is far below that of air at Earth's surface, and far below that of any solid or liquid familiar in everyday life. Even this statement understates the contrast, because the outer atmosphere itself is much less dense than the average. The star is not a giant compact object filling its whole volume with thick substance. It is an extended gravitational structure in which a concentrated interior supports an atmosphere so spread out that the concept of a sharply bounded body begins to lose clarity. This low density has visible and physical consequences. A diffuse outer envelope is weakly bound compared with the deeper stellar interior. Gravity still holds it, but not with the tight grip seen in smaller, more compact stars. As a result, the atmosphere is more easily disturbed by convection, radiation pressure, pulsation, and the mechanical effects of waves moving upward from below. Large rising and sinking currents can travel through the outer layers. Surface regions may cool or warm unevenly. Matter can be lifted outward and sometimes lost entirely in slow winds. These effects are not secondary details. They are part of what it means for the star to be so large. Vast size and low density go together. The same expansion that creates the star's extraordinary radius also weakens the cohesion of the outer envelope and makes instability more likely. The relation between radius and mass also becomes clearer when compared with smaller stars. The Sun, for example, contains far less mass than a red hypergiant at birth, yet it is much more compact because its present evolutionary stage does not require a hugely inflated envelope. In contrast, Stevenson 2-18 began life as a far more massive star and has evolved into a stage where energy transport and core structure force the outer layers to expand dramatically. Even so, the star may now have lost a substantial amount of mass through stellar winds over the course of its life. Massive stars do not remain closed systems. They shed material continuously, and the most evolved among them may lose matter at especially high rates. This means the current mass of Stevenson 2-18 is not simply the initial mass it possessed when it formed. It is the remaining mass after long periods of internal burning, mixing, and atmospheric loss. A hypergiant can therefore be both one of the largest stars known and at the same time less massive than many people might imagine from size alone. This helps explain why the outer layers can stretch so far. The atmosphere does not need to be dense to be luminous. What matters for the visible appearance is that the gas remains opaque enough in a certain region for photons to emerge and define a photosphere. Because the outer material is cool and extended, a vast area can radiate even when each local region contains relatively little matter. The star's brilliance comes from enormous surface area, combined with continued energy flow from the interior, not from the outer layers being thick or tightly packed. In effect, the star's visible form is a giant luminous skin wrapped around a much more centrally concentrated body. That skin is not detached from the interior, but its structure reflects a delicate balance between gravity pulling inward and pressure from heat and radiation supporting it from below. The imbalance is never far away. Small changes in temperature, opacity, or internal energy transport can reshape portions of the envelope. This diffuse structure also makes measurement difficult. When astronomers estimate the radius of Stevenson 2-18, they are measuring the location of an effective surface in an atmosphere with no hard edge. A denser star presents a simpler boundary. A hypergiant presents a gradient, and that gradient can shift. In a sense, the star's enormous size is partly a property of where the atmosphere becomes observable, rather than where matter suddenly stops. This is another reason why the radius can be uncertain, and why discussions of the largest known star must remain somewhat provisional. The physical object is real, but its boundary is not defined with the precision one might expect from solid bodies or compact stars. There is also an evolutionary meaning to this thin vastness. A star does not become a red hypergiant by accident. It reaches this stage because deep changes in the core alter the balance of the whole star. As fusion proceeds through advanced stages, the core contracts and heats, while the envelope responds by expanding and cooling. The outer layers become the visible sign of deeper internal exhaustion. Their low density is therefore not merely a structural curiosity. It is evidence that the star is living in a late and unstable state. Size, in this context, is not strength. It is a symptom of transition. Stevenson 2-18 appears colossal because much of its outer matter has been spread across an enormous volume that gravity holds only loosely. The very features that make it seem overwhelming in scale also make it fragile. Beneath the giant radius lies a simpler truth. The star is not filled with solid abundance, but with thin extended atmosphere, luminous because it is broad, unstable because it is diffuse, and already moving toward the next, more violent stage of its existence. Even after Stephenson 2-18 comes to be described as one of the largest stars ever identified, that description remains tied to an important scientific caution. Extreme stars do not sit in a neat and permanent ranking the way mountains might sit on a fixed survey of Earth. Their measured sizes depend on distance estimates, extinction corrections, spectral interpretation, atmospheric models, and the difficult problem of defining what counts as the visible surface of a very diffuse star. Because of this, the title of a largest known star is less like a settled crown, and more like a temporary position within a shifting boundary of observation. Stephenson 2-18 stands near that boundary, but it does not stand there alone. Other enormous red supergiants and hypergiants have also been proposed as rivals, and the comparison among them reveals how astronomy measures extremes under uncertainty. Among the most frequently discussed contenders are stars such as UY Scuti, WOHG 64, Westerlund 1-26, and V Canis Majoris. Each of these objects has, at one time or another, been cited as one of the largest stars known. Each is a highly evolved luminous giant with an extended atmosphere and significant observational complications. Their names often circulate in popular accounts as if the question was simply which one has the biggest number attached to its radius. In practice, the comparison is more delicate. Some of these stars lie in crowded regions. Some are embedded in heavy circumstellar dust. Some show substantial variability. Some have poorly constrained distances. In every case, the inferred radius depends on how astronomers combine imperfect observations into a physical model. Stevenson 2-18 enters this rivalry not because it is the only huge star, but because its estimated radius reaches the very upper end of what current observations seem to allow for a cool, evolved star. This creates a natural temptation to speak in absolutes. Yet the science becomes more interesting when the caution is preserved. The first source of difficulty is distance. A star's luminosity depends strongly on how far away it is. If a star is thought to be more distant, then its true energy output must be greater in order to produce the observed brightness at Earth. Greater luminosity, combined with similar temperature, implies a larger radius. If the distance is later revised downward, the estimated radius shrinks. This is not a small effect. For the largest stars, even moderate changes in the adopted distance can alter the final ranking substantially. Stephenson 2-18 benefits from membership in a known cluster, which helps anchor its distance more securely than for some isolated giants. But even cluster distances in the inner Milky Way remain subject to refinement. That means any claim about its exact position among record holders is conditional on the best current cluster parameters rather than immune to change. A second difficulty lies in extinction and reddening. The light from these stars travels through interstellar dust, and in many cases through dust produced by the stars themselves. Correcting for that obscuration is essential when estimating total luminosity, but the dust is often clumpy, asymmetric, and wavelength dependent in ways that are not perfectly uniform. A small change in the adopted extinction law can produce a different luminosity estimate, and therefore a different radius. This matters especially for stars observed mainly in infrared wavelengths, where the atmosphere and surrounding dust can both influence the interpretation. Stevenson 2-18 is hidden behind substantial intervening material, so its luminosity estimate cannot be separated from the quality of those corrections. Another challenge is effective temperature. For compact stars with relatively simple atmospheres, temperature can often be estimated with fairly high confidence. For red hypergiants and red supergiants, the atmosphere is far more complex. Molecules form. Large convective cells distort the surface. Pulsation changes the outer layers, and circumstellar material can alter the observed spectrum. The notion of a single effective temperature remains useful, but it is an idealized summary of a very complicated photosphere. Since radius depends on both luminosity and temperature, any uncertainty in temperature feeds directly into uncertainty in size. A slightly warmer adopted temperature can reduce the required radius for a given luminosity, while a slightly cooler one can enlarge it. In stars at the edge of the known size range, that shift can matter greatly. The most subtle problem of all may be the meaning of radius itself. In ordinary language, radius implies a clean geometric boundary. In a red hypergiant, there is no such sharp edge. The atmosphere thins gradually, and the apparent size depends on wavelength, opacity, and the depth from which photons escape. One observer may define the radius at one optical depth. Another model may treat the atmosphere differently, and the resulting values may both be reasonable within their assumptions. This makes the competition among stellar giants somewhat unlike a race measured to exact fractions. It is more like comparing coastlines whose edges blur into mist. The stars are undeniably enormous, but the final figure is not the same kind of number as the radius of a solid planet. This is why some famous record claims in astronomy later soften or shift without scandal. The change reflects improving understanding rather than failure. Rival giants highlight this pattern. UY Scuti has often been presented as the largest known star in popular summaries, yet published estimates of its radius span a range that depends strongly on method. V Canis Majoris was once thought to be even larger than many later studies support, because improvements in distance and atmospheric interpretation change the result. WOHG 64, located in the Large Magellanic Cloud, presents its own complexities linked to heavy mass loss and surrounding dust. Westerlund 1-26 is another remarkable evolved star in a massive cluster, but its size and luminosity also depend on difficult observational interpretation. Stevenson 2-18 does not escape these same issues. What makes it important is that, even under cautious treatment, it remains among the most extreme known examples. The ranking may shift, but the extremity does not disappear. There is also a deeper lesson in this rivalry. The question is not only which star is marginally larger, it is what these stars together reveal about the upper envelope of stellar expansion. When several objects cluster near a similar maximum scale, they suggest that stellar physics itself is imposing a limit. The uncertainties from one star to another do not erase that pattern, they sharpen it. Stevenson 2-18 and its rivals show that massive stars can inflate to radii of roughly 2,000 solar radii or somewhat beyond, but not without entering a regime of heavy instability, low surface gravity, and intense mass loss. In that sense, the record book is less important than the boundary line it traces. Stevenson 2-18 matters not because it conclusively defeats every rival under every model, but because it occupies the frontier where measurement, theory, and atmospheric complexity all meet. It is a contender in a category that is inherently difficult to define. Yet its place near the top is supported by enough evidence to make it one of the clearest symbols of stellar excess. The uncertainty surrounding its title does not weaken its significance. It reveals the true nature of astronomy at the edge of observation, where the larger stars are not measured as simple objects, but interpreted as living atmospheres whose extremes can only be approached with humility. The existence of several giant contenders near the same upper range of size suggests that the larger stars are not unlimited in how far they can expand. Stevenson 2-18 is enormous, but it does not imply that a star can grow without bound so long as enough fuel remains in the core. Stellar physics resists that idea. A star is held together by gravity and supported from within by pressure generated through heat and radiation. In most stages of stellar life, these forces maintain a workable equilibrium, though never a static one in the strict sense. In the most extreme red hypergiants, however, that balance becomes difficult to preserve. The star expands until its outer layers are weakly bound, easily disturbed, and increasingly vulnerable to escape. The question is not merely how large a star can become, but how large it can remain while still functioning as a coherent stellar atmosphere, rather than dissolving into instability and mass loss. One of the main limits comes from gravity itself becoming less effective in the outer layers as the radius increases. Surface gravity falls rapidly with distance from the centre, in a star whose photosphere lies at a vast radius. The pull on gas near the visible surface is far weaker than in a compact star. That weak binding makes it easier for the atmosphere to swell, but it also makes it easier for the atmosphere to be perturbed and lifted outward. The same expansion that produces giant size also undermines the long-term stability of that size. At some point, the star's outer envelope becomes so weakly held that convection, pulsation, radiation pressure, and local opacity changes can drive matter away. The star can still appear huge, but its size begins to come with a cost. The envelope leaks. Another important limit involves luminosity. Massive evolved stars are intensely bright, and that brightness exerts outward force through radiation. Photons carry momentum as well as energy, so when they are absorbed or scattered by gas and dust, they push outward on the material. If the luminosity grows too large compared with the star's mass, radiation pressure can approach the inward pull of gravity. This does not necessarily blow the whole star apart at once, but it makes the outer layers increasingly unstable. The relevant concept is often linked to the Eddington limit, which describes the point at which radiative force balances gravitational attraction in an idealized case. Real stars, especially cool hypergiants with complex atmospheres, do not follow that simple formula in a perfectly direct way, yet the underlying principle remains important. A star close to this limit finds it harder to keep its outer layers bound. The closer it comes, the more likely it is to lose matter. Stevenson 2-18, with its immense luminosity and low surface gravity, lives close to that difficult regime. Opacity adds another layer to the problem. The outer atmosphere of a cool, massive star is not a simple transparent shell. Its gas contains atoms, ions, and molecules whose ability to absorb radiation changes with temperature and density. In certain zones, opacity can increase significantly, meaning radiation is trapped more effectively and exerts more outward influence on the local gas. This can create unstable layers where energy transport becomes inefficient or where material is pushed outward more strongly. In effect, The envelope develops regions that are easier to inflate but also harder to hold together. The physics of these layers is complicated, especially when convection and pulsation are also present. But the broad consequence is clear. A very large cool star sits in an atmospheric regime where the outer structure is especially sensitive to small internal imbalances. That sensitivity helps explain why the larger stars are also among the most variable and unstable. Mass loss is the practical expression of these limits. A star can expand toward an enormous radius, but if the price of doing so is strong outflow, then the very act of becoming larger also starts to erode the conditions that allow that size to persist. Winds carry away mass and angular momentum. Dust formed in the outflow absorbs and re-radiates energy. Episodic eruptions may remove portions of the envelope more rapidly than steady winds alone. Over time, this loss can alter the star's luminosity to mass ratio, change its surface chemistry, and shift its evolutionary path. In that sense, the larger stars are often self-correcting systems. The more extreme the envelope becomes, the more vigorously the star tends to shed it. This is one reason why stars do not simply inflate forever into larger and larger red forms. The physics of support eventually becomes the physics of escape. Convection also plays a major role in setting practical limits. In cool hypergiants, the transport of energy through the outer layers is dominated not only by radiation, but by enormous convective motions, rising and sinking currents of gas that can span a significant fraction of the stellar radius. These currents are not the small cellular patterns seen on compact stars. They may be vast regions of upwelling and downflow that distort the surface temperature and density structure on very large scales. Such motions undermine the ideal of a smooth, symmetric atmosphere. They create local imbalances, change opacity patterns, and may help launch mass outward. A star that is too large becomes difficult to maintain as a quiet sphere because its own energy transport becomes turbulent across an enormous diluted envelope. This is not merely an observational nuisance. It is part of the reason the upper size range of stars appears to cluster within a limited band, rather than continuing upward without restraint. There's also a nuclear timescale limit. The red hypergiant phase is brief compared with the main sequence. Massive stars evolve rapidly, and the later stages of fusion in the core proceed faster than the earlier ones. A star may reach its greatest radius only for a relatively short span before further core evolution or mass loss shifts it toward another state. This means that even if conditions briefly allow exceptional size, the star may not remain in that form long enough to be common. The rarer stars are not only hard to form, they are hard to catch in the act. Stevenson 2-18 therefore represents both a physical extreme and a fleeting moment in the life of a massive star. The fact that it is seen at all is part of what makes it valuable. All of these processes together define the upper frontier of stellar expansion. Gravity weakens outward, radiation presses upward, opacity complicates support, convection distorts the envelope, mass loss strips away the very layers that create the giant radius. Time runs short. The larger stars occupy a narrow and unstable compromise among these competing forces. Stevenson 2-18 sits near that compromise. Its enormous radius is not proof that stellar size has no ceiling. It is evidence that the ceiling itself lies in a domain of fragility, where the star can become breathtakingly large only by approaching the point at which its outer layers begin to fail. In this sense, the star does not merely challenge the limits of stellar physics, it helps define them. By the time a star reaches the conditions seen in Stephenson 2-18, its enormous outer form is no longer the defining event of its life, but the visible consequence of deeper changes already underway in the interior. The star begins as a massive main sequence object, compact compared with its later self, sustained by the fusion of hydrogen into helium in the core. During that long earlier phase, outward pressure from the energy released by nuclear burning balances the inward pull of gravity with relative stability. The star is luminous and short-lived compared with the Sun, but it remains structurally coherent. Over time, however, the hydrogen in the central region is depleted. Once core hydrogen burning ends, the balance that has supported the star through most of its life begins to shift. The core contracts under gravity, heats further, and prepares for new stages of nuclear fusion. The outer layers, responding to the changed interior, expand. This is the essential pattern that eventually produces the red hypergiant state. Expansion of the envelope and contraction of the core occur together as linked parts of the same evolutionary transition. The core and envelope do not evolve in the same direction. The center becomes denser, hotter, and more compressed, while the visible body of the star becomes cooler, larger, and far more diffuse. This contrast is one of the central facts of late stellar evolution. The star looks swollen from the outside because it is moving toward exhaustion on the inside. In a massive star, the core after hydrogen burning can ignite helium, converting it into heavier elements such as carbon and oxygen. For the most massive stars, still later stages of burning follow in increasingly rapid succession, involving carbon, neon, oxygen, and silicon in nested shells or central regions depending on the exact moment in the star's evolution. Each new stage requires higher temperature and greater compression than the one before. The timescales shorten dramatically. What once lasted millions of years gives way, in later phases, to intervals that are progressively briefer. The red hypergiant form belongs to this advanced era of stellar life, when the interior is already moving through a sequence of accelerated transformations. The outer swelling of Stevenson 2-18 is therefore not a separate phenomenon from nuclear evolution. It is the atmospheric expression of the star's internal restructuring. As the core contracts and heats, the energy flow through the star changes. Shell burning outside the core can become especially important, adding luminosity and altering the pressure balance in the envelope. The outer layers respond by moving outward until they settle, never perfectly, into a cooler and more extended configuration. The drop in surface temperature shifts the visible color toward deep red, even as the total luminosity remains immense. This is why a red hypergiant can be both cool at the surface and among the most powerful stars in the galaxy. The energy comes from the interior, but the outer envelope spreads that energy across a much larger area. In this sense, the star becomes physically larger because it is evolutionarily older. Youth in massive stars belongs to compact brilliance. Old age belongs to swollen instability. The word hypergiant is used for stars of exceptional luminosity and extreme atmospheric conditions, often accompanied by significant mass loss and instability. Stevenson 2-18 fits this broader picture. It is not merely a red supergiant scaled upward by a simple factor. It appears to occupy the upper edge of the evolved cool luminous population, where the envelope has expanded to extraordinary size and the atmosphere is increasingly difficult to keep bound. That status suggests a star near the end of its red phase, or at least deep within the most advanced portion of it. Exactly where it sits along that late path can be difficult to specify with precision, because the observable surface tells only part of the story, and the evolutionary tracks of massive stars depend on mass loss, rotation, internal mixing, and metallicity. Even so, the broad interpretation is secure. Stevenson 2-18 is a massive star in transition toward its terminal fate, already far removed from the quieter stability of its youth. This transitional nature explains why the star's appearance can be misleading if treated as permanent. The enormous envelope is real, but it is not the final stable shape of the star. It is one temporary response to deep internal processes that are moving toward collapse. Massive stars do not end their lives as immense cool spheres. They pass through such phases while the core continues to evolve toward heavier elements and diminishing returns from fusion. The paradox is that the star appears grandest in outward size when its inward options are narrowing most severely. The core becomes more compact and more complex, building layers of ash and active burning zones like nested shells. The outer atmosphere, meanwhile, drifts farther from the center and becomes more weakly bound. The star acquires the appearance of grandeur at the same time that its structural vulnerability increases. Convection intensifies this transitional state. In a greatly expanded envelope, heat cannot be carried outward by radiation alone with perfect efficiency. Large convective currents arise, transporting energy through rising and falling gas over vast distances. These motions contribute to the irregularity of the surface and may enhance mixing between layers. They also help explain why the hypergiant phase is not a quiet one. A star in this state is not settling into a serene final shape. It is adjusting continuously to changing interior conditions. Pulsation, episodic outflow, and local surface variation are not accidents imposed from outside. They belong to the star's evolutionary status. It is in motion because its core is in motion. Mass loss is another sign that the transition is advanced. As the envelope expands and surface gravity weakens, winds can carry matter away at increasing rates. This lost material alters the future evolution of the star by reducing the envelope mass and exposing deeper processed layers over time. In some massive stars, sufficiently strong loss can even move the star away from the red hypergiant phase and toward a hotter stripped state before final collapse. Whether Stevenson 2-18 will follow such a path with dramatic reversal or remain broadly cool until close to the end remains uncertain, but the possibility itself shows how transitional the phase is. The star is not sitting at an endpoint. It is passing through an unstable corridor shaped by the competition between continued expansion and progressive erosion. The cluster environment reinforces this interpretation. Stephenson 2 contains many red supergiants, indicating a population of massive stars at similar evolutionary age, though not identical mass. Stephenson 2-18 stands out because it appears among the most extreme of them. That extremity suggests it represents either one of the most massive original stars in the group, or one whose evolution has driven it farther into the swollen late state than most of its companions. In either case, it becomes a marker of what happens when massive stellar evolution reaches one of its widest and most unstable visible expressions. The giant radius is not the beginning of the story. It is the late visible chapter of a star that has already consumed its central hydrogen, reorganized its interior, built a contracting core, and inflated an atmosphere that can no longer hide how near the end it has come. Stephenson 2-18 appears majestic because it is in transition, and it is in transition because the long inward work of stellar evolution has pushed the star toward a final act that the swollen envelope can only briefly postpone. In a star as expanded and weakly bound as Stephenson 2-18, the outer atmosphere does not remain smooth or still for long. The immense envelope is in constant motion, shaped by processes that are large in scale, slow in rhythm, and yet persistent enough to alter the star's appearance and future. This instability is not an accidental disturbance imposed on an otherwise quiet giant. It is a natural consequence of the star's low surface gravity, extreme luminosity, diffuse outer layers, and advanced evolutionary state. A compact star can preserve a relatively orderly surface because its gravity keeps the atmosphere tightly bound and its energy transport remains confined within a smaller volume. A hypergiant lives under very different conditions. Its atmosphere stretches over a vast radius where gravity has weakened, and the energy flowing outward from the interior must cross layers too extended and too delicate to remain uniform. The result is a star whose visible surface behaves less like a stable shell and more like a restless weather system on a cosmic scale. One of the main drivers of that restlessness is convection. In the outer envelope of a cool, massive star, radiation alone does not carry energy outward with complete efficiency. Large packets of hot gas rise, cool, and sink again, transporting energy through motion. In the Sun, convection appears as a fine cellular texture across the surface. In a red hypergiant, the same basic process occurs on an immensely larger scale. The convective cells may occupy a substantial fraction of the stellar radius, instead of many small granules. The star may host only a few enormous regions of upwelling and downflow at any given time. These giant currents create temperature differences across the photosphere, making some areas brighter, others cooler, and none perfectly steady. The surface that appears from a great distance as a single red glow may in reality be mottled, irregular, and changing over time. Such convective activity affects not only brightness, but also the atmosphere's structure. Gas lifted by rising currents can reach regions where the local gravitational binding is already weak. There it may linger, cool, or begin to drift outward. This helps create a connection between internal energy transport and mass loss. The star does not need a single violent eruption to shed material. Its own ordinary, though extraordinary in scale, convective behavior can help launch matter into the surrounding space. In this sense, the atmosphere is continually trying to rearrange itself, and some of that rearrangement results in permanent loss. Pulsation adds another layer to the instability. Many evolved luminous stars undergo rhythmic expansion and contraction, driven by changes in pressure, opacity, and internal energy flow. These pulsations need not be perfectly regular like the motion of an ideal clock. In a hypergiant they may be multiple, shifting, and partly chaotic, interacting with convection and atmospheric stratification. The whole star or large parts of its envelope can alternately swell and fall back on timescales of months to years. Such motion changes the radius, temperature, and brightness at least slightly over time. For Stevenson 2-18, variability is expected in this general sense, even if every detail of its pulsational pattern is not yet firmly pinned down. A star of such extreme size and low density envelope would be surprising only if it were stable. Variability is part of its identity. The atmosphere may also be shaped by shock waves moving outward through the gas. When pulsation and convection interact in a weakly bound envelope, compressions can travel through the atmosphere, heating and accelerating matter locally. These disturbances do not necessarily produce spectacular explosive events in every cycle, but they contribute to a rough, uneven outer structure. Some regions may become denser and cooler, encouraging molecule or dust formation farther from the star. Other regions may be more transparent or more strongly accelerated. The result is not a uniform wind flowing from a perfectly spherical surface. It is an outflow marked by clumps, asymmetries, and changing velocity from one region to another. Observations of other red supergiants and hypergiants support this picture of highly structured mass loss, and Stevenson 2-18 likely belongs to the same broad physical regime. Magnetic fields may also play a role, though their exact influence in stars like Stevenson 2-18 remains less certain than the effects of convection and pulsation. In evolved cool stars, magnetic activity can arise through motions in ionized gas and may help shape local outflows or atmospheric structure. Yet the outer envelopes of red hypergiants are so extended and dynamically complex that magnetism is difficult to isolate as a dominant driver. It is more likely one participant in a wider pattern of instability than the single controlling force. Observations indicate that the star loses material, but the detailed contribution of magnetic processes, compared with pulsation, radiation pressure, and convection, remains an active area of interpretation rather than a settled conclusion. The stellar wind itself is one of the clearest outcomes of this restless surface. Material from the outer envelope flows outward at comparatively modest speeds by stellar standards, but because the star is so luminous and the envelope so extended, the cumulative mass loss can still be substantial. Over time, this drifting matter forms a circumstellar environment of gas and dust around the star. Infrared observations are especially sensitive to such environments because dust absorbs the star's radiation and re-radiates it at longer wavelengths. This means that part of the infrared prominence of stars like Stephenson 2-18 may come not only from the cool photosphere, but also from surrounding material previously shed by the star itself. In this way, the star begins to build the medium into which its later death will occur. It surrounds itself with a record of its own instability. The mass loss is not merely a surface detail. It changes the star's future as matter escapes. The ratio between luminosity and remaining mass shifts, often making the outer layers even harder to hold. Surface abundances may change as deeper processed material is exposed or mixed outward. The path toward final collapse can be altered by how much envelope mass is removed before the core reaches its terminal state. In some massive stars, this process can lead to transitions toward hotter phases. In others, the star may remain broadly cool while steadily eroding. For Stevenson 2-18, the exact path remains uncertain, but the general direction is clear. A star of this kind is not keeping its giant form intact. It is gradually unmaking it. The significance of this instability lies in its scale. On Earth, weather and turbulence belong to atmospheres wrapped around solid worlds. In Stevenson 2-18, the atmosphere is the star's visible body. There is no stable ground beneath the storm. The motions of gas, the lifting of matter, the slow pulsations, the clumpy wind, and the formation of dust are not happening on top of the star. They are the way the star now exists. The giant radius seen from afar is only the average outline of a body whose outer layers are already in partial retreat. Stevenson 2-18 appears majestic because of its size, but that size is maintained by a fragile and unsettled envelope. The same processes that give it form are already carrying pieces of that form away into space, for all its vastness and instability. Stevenson 2-18 is not a permanent structure. The same internal evolution that inflates its envelope also prepares its end, and that end is expected to be violent. Massive stars do not fade quietly into compact remnants the way smaller stars eventually do. Their cores continue fusing heavier and heavier elements until the process reaches a final barrier. Fusion can release energy when light elements combine into heavier ones, up to the production of iron group nuclei. But beyond that point, the balance changes. Building still heavier elements no longer provides the outward energy needed to support the core against gravity. Once a sufficiently massive core becomes dominated by iron-rich material, the star approaches a crisis that no adjustment of the outer envelope can prevent. The giant red atmosphere of Stephenson 2-18 may still stretch across a region comparable to planetary orbits, but the decisive events now belong to the compact, hidden centre far beneath that visible surface. In the late stages of a massive star's life, burning proceeds in shells around the core with extraordinary complexity. Hydrogen may continue in an outer shell, helium burns deeper in, and still farther inward, successively heavier fuels are consumed in ever hotter, denser layers. The structure becomes stratified, often compared to nested shells, with each zone representing the ash of earlier burning or the active fusion of a new element. Yet this elegant layering is temporary. Every advanced burning stage is shorter than the last, carbon burning lasts far less time than helium burning. Neon, oxygen, and silicon burning unfold faster still. What once took millions of years contracts towards centuries, years, months, or less, depending on the stage and the exact mass of the star. The great swollen form of Stephenson 2-18 therefore belongs to a period when the outer appearance may seem slow and grand, while the core is moving through increasingly rapid transitions toward collapse. The terminal moment arrives when the core can no longer support itself. As iron accumulates and fusion ceases to provide effective outward pressure, gravity wins. The core collapses inward in a fraction of a second. Electrons and protons are crushed together, forming neutrons and releasing a flood of neutrinos. The collapsing inner region overshoots, stiffens under nuclear forces, and may generate a rebound, though the full physics of how the explosion is launched remains one of the most difficult problems in stellar astrophysics. The broad picture is well established. A massive star's core collapses, an outward shock is produced or revived, and the surrounding layers are blasted into space in a supernova. For Stephenson 2-18, that is the most widely expected fate. Exactly when it will happen cannot be predicted on human timescales. In cosmic terms, the event may be relatively near, perhaps within the next hundreds of thousands or low millions of years, but in human terms that is not soon. The star is dying, but not imminently in any practical sense for present observers. The form of the supernova remains less certain than the fact of catastrophic ending. A cool red hypergiant with a massive extended envelope is often associated with the broad family of core collapse supernovae, especially those in which hydrogen is still present in the outer layers at the moment of explosion. Yet strong pre-supernova mass loss can alter the exact classification. If enough of the envelope is removed before collapse, the event may differ significantly from the simplest red supergiant expectation. Dense circumstellar material could also reshape the appearance of the explosion if the blast wave collides with matter previously shed by the star. In that case, the star's long period of instability would help script the visible character of its final outburst. Stevenson 2-18 may therefore die not in isolation, but within an environment it has been building around itself through wind and mass loss. The remnant left behind depends mainly on the final mass of the collapsing core. If the core after collapse can be supported by neutron degeneracy pressure, the result is a neutron star, an object of extraordinary density compressed into a sphere only a few tens of kilometers across. If the core is too massive for even that support, collapse continues and a black hole forms. For a star as extreme as Stephenson 2-18, both outcomes are discussed as possibilities. The present uncertainty reflects the fact that the initial mass, current mass, lifetime mass loss, and internal evolution are not known with complete precision. A star that begins very massive may nevertheless lose enough material before core collapse to leave a neutron star rather than a black hole, while another may retain a core too heavy to avoid further collapse. The star's visible enormity does not by itself decide the matter. The final answer lies in the hidden mass and structure of the core at the moment the outward support fails. What is certain is that the outer giant will not survive in its present form. The supernova will tear apart the envelope and scatter newly enriched material into the surrounding cluster and galaxy. Elements forged over the star's lifetime, along with others produced or redistributed in the explosion itself, will be expelled into space. The energy released in that brief event will outshine the entire present output of the star by an immense factor, though only for a short period. The quiet red giant that now seems almost slow in its scale will end in a flash of destruction far more violent than its current appearance suggests. This contrast is one of the defining truths of massive stellar evolution. The most languid-looking stars can meet the most abrupt deaths. there is also a wider astrophysical importance to this fate. The death of a star like Stephenson 2-18 is not merely the loss of an individual object. It is part of the mechanism by which galaxies are renewed. Supernovae inject heavy elements, kinetic energy, and shock waves into the interstellar medium. They can compress nearby gas, contribute to future star formation, and alter the chemistry of the regions around them. In a young massive cluster such as Stephenson 2, repeated deaths of massive stars gradually transform the local environment. Stephenson 2-18 is only one member of that larger story, but because of its extremity, it serves as a striking example of how stellar grandeur ends. Its current size, its instability, its heavy winds, and its uncertain rank among giant stars all point toward the same conclusion. The star is not settling into permanence. It is approaching a final structural failure that no expanded envelope can resist. Beneath one of the largest visible stellar forms known, the compact core is moving toward the moment when gravity will overturn the whole star. When that happens, the giant will disappear, and in its place there will remain only an expanding remnant, enriched debris, and either a neutron star or a black hole where the center once held. Stevenson 2-18 does not exist alone in the galaxy. It belongs to Stevenson 2, one of the richest known clusters of red supergiants in the Milky Way, and that setting gives the star a broader meaning than it would have in isolation. A cluster is not simply a loose gathering of stars that happen to occupy the same line of sight. It is a population born from the same giant cloud of gas, formed at roughly the same time, and therefore linked by shared age, shared origin, and often similar chemical composition. In a young massive cluster, the most luminous and short-lived stars evolve first, leaving behind a visible pattern of stellar aging that can be read across the group. Stevenson 2 is remarkable because that pattern includes an unusually large population of red supergiants, each one representing a brief late stage in the life of a massive star. Stephenson 2-18 appears as one of the most extreme members of this family, but the family itself is part of the story. The cluster provides the environment from which the star emerges and the context in which its fate becomes significant. Massive clusters are natural laboratories for stellar evolution, because they allow astronomers to compare stars that begin under similar initial conditions. In the field of the galaxy, an isolated red supergiant can be difficult to interpret. Its age, distance, and birth environment may be uncertain. Inside a cluster, many of those uncertainties are reduced. The stars share a common birthplace and roughly the same age, so differences among them can be traced more directly to differences in initial mass, rotation, mass loss, or internal mixing. Stephenson 2 is therefore valuable not only because it contains extraordinary stars, but because it contains many of them together. The cluster shows what a generation of massive stars looks like. When viewed at the moment, some members have already reached advanced red phases while others occupy slightly less evolved states. In that setting, Stephenson 2-18 becomes more than a solitary giant. It becomes a marker of the extreme upper edge of a shared evolutionary population. The cluster itself is likely only a few tens of millions of years old, young by the standards of most stars but old enough for the most massive original members to have left the main sequence. That age is consistent with the presence of many red supergiants. Stars massive enough to enter this phase do not live long. They burn their fuel quickly and evolve rapidly. Their presence together in Stephenson 2 indicates a burst of star formation that once produced a substantial population of high-mass stars, many of which are now nearing the end of their lives. Some of the cluster's earliest and most massive members may already have exploded as supernovae, leaving behind compact remnants and enriching the surrounding medium long before the present moment. The red supergiants visible today including Stephenson 2-18, are therefore survivors from an original stellar generation that was likely even richer and more extreme than the current population suggests. This perspective changes the way the giant star is understood. Stephenson 2-18 is not an isolated accident. It is one outcome of a clustered mode of massive star formation, in which many heavy stars are born together and then evolve in parallel but not identically. Some remain somewhat less extreme in size or luminosity. Others may lose mass more rapidly. One star, because of its initial mass or evolutionary history, may swell farther than the rest and become the dominant giant in the group. Yet all are linked by a common origin. The cluster turns individual stellar evolution into a collective history. It also gives the future explosion of Stephenson 2-18 a local setting. When the star finally dies, it will not deposit its material into an empty and anonymous region of space. Its ejector will enter an environment already shaped by other massive stars, stellar winds from neighbouring red supergiants, earlier supernova remnants, ionized gas, and the collective gravitational loosening of the cluster over time will all contribute to the structure of the surrounding medium. The death of the star will therefore become part of an ongoing transformation rather than a single isolated event. Massive clusters do not remain tightly bound forever. As their stars evolve, lose mass, and sometimes explode, the total gravitational binding of the cluster can weaken. Encounters among stars and tidal forces from the Milky Way gradually stretch and disperse the population. Over millions of years, the cluster's original compactness can be reduced, and its members begin to blend into the broader field of the galaxy. Stephenson 2 will not remain eternally recognizable as a distinct stellar city. Its stars will age, die, or drift away. The red supergiant population that now makes it remarkable is itself temporary, a brief moment in the much longer history of dispersal and galactic mixing. In that sense, the cluster and its greatest star share a similar fate. Both are transient concentrations. Both seem grand now because they are being observed during a narrow interval, when their most luminous members are still present. The material returned by Stephenson 2-18 and its cluster companions will help enrich the wider galaxy. Carbon, oxygen, silicon, calcium, iron, and many other elements forged in massive stars do not remain locked inside them forever. Through winds and supernovae, that material is returned to interstellar space, where it mixes with gas that may later form new stars, new planets, and new chemistry. The cluster therefore functions as a localized engine of galactic change. Its members convert primordial or recycled gas into structured stellar lives, and then return processed matter to the medium from which later generations will emerge. Stephenson 2-18 is one especially dramatic part of that exchange, but the whole cluster participates in it across time. There's also a human significance in studying such a population. Because Stephenson 2 contains so many red supergiants, it helps astronomers test how massive stars evolve as a group, rather than only as isolated case studies. The cluster constrains models of age, initial mass, mass loss, and evolutionary timing. It raises questions about how many red supergiants a massive cluster can host at once, what that implies about the original stellar distribution, and how stars near the upper mass range move through their late phases. Stephenson 2-18 draws attention because of its enormous radius, but it gains scientific strength from belonging to a cluster that supplies comparison, context, and collective evidence. The giant star is the most dramatic figure in the scene, yet the scene itself explains why that figure matters. In the end, the cluster setting restores proportion to the record of the star. Stephenson 2-18 may appear singular because of its size, but its story is tied to many neighbouring massive stars born from the same cloud and aging under the same galactic conditions. Its future explosion will become one more chapter in the gradual unmaking of the cluster and the wider enrichment of the Milky Way. The giant is extraordinary, but it is not separate. It belongs to a temporary society of massive stars whose brief brilliance will disperse into the galaxy that formed them. For all the grandeur of Stevenson 2-18 and the drama of its eventual death, the star is a profoundly poor setting for planets, and an even poorer setting for life. This conclusion does not follow from any single hostile feature alone, but from the whole pattern of what such a hypergiant is. It is massive, short-lived, unstable, intensely luminous, and surrounded by an environment shaped by strong winds and heavy mass loss. These properties make the star scientifically important, yet they also make it almost the opposite of what is usually associated with long-term planetary stability. The elements needed for life may be forged in massive stars and spread by their deaths, but the stars themselves are not gentle homes for biology. In the case of Stevenson 2-18, the contrast is especially stark. The very processes that make the star one of the largest known also make it dynamically violent and evolutionarily brief. Planet formation begins in disks of gas and dust around young stars. In principle, many kinds of stars can possess such disks in their youth. Massive stars, however, create difficult conditions from the start. They emit intense radiation, produce strong stellar winds, and evolve quickly. The disk around a high-mass star faces erosion, heating, and disruption long before slow planet-building processes can proceed in a calm and efficient way. Even if planets begin to form, they do so in a harsh radiative environment, where volatile materials are easily lost and orbital conditions are subject to disturbance, around a star destined to become a red hypergiant. The problem is not only present conditions but future change. The star does not remain stable for billions of years, as smaller stars often do. It races through its life. Any planetary system would have to endure not only the star's fierce youth, but also its radical transformation into an expanded and unstable giant. The timescale alone is devastating to the prospect of life as commonly understood. Complex life on Earth requires billions of years of comparatively stable conditions. Massive stars do not offer such patience. They live for only millions or tens of millions of years before ending in collapse. That span may be long by human standards, but it is short in biological and geological terms. Even if a rocky planet could form and remain bound, the window for long-term climatic stability would be narrow. Before any slow evolutionary process could unfold, the host star would already be changing in luminosity, radius, and radiation environment. A star like Stevenson 2-18 therefore fails one of the simplest requirements for life-bearing worlds' duration. It does not stay suitable for long enough. The star's late expansion makes the situation far worse. As the core evolves and the outer envelope swells into a red hypergiant, the inner planetary system, if one existed, would be engulfed or catastrophically heated. Orbits once safely distant in the main sequence phase could become embedded within the outer atmosphere. The region around the star would be redefined by drag, intense heating, radiation, and tidal effects. Planets in close or moderate orbits would not simply become warmer. They would cease to be ordinary planets at all. Their surfaces would vaporize, atmospheres would be stripped or chemically transformed, and their orbital energy could be altered by interaction with the extended stellar envelope. Even worlds far outside the visible surface would not inhabit a calm environment, because the swollen star loses mass and changes luminosity, altering the gravitational and radiative balance across the whole system. Instability, not habitability, becomes the defining condition. The circumstellar environment is also hostile. Stevenson 2-18 is expected to shed matter in winds and clumps, surrounding itself with gas and dust that reflect a long period of atmospheric erosion. This material can reshape local radiation fields, generate shocks, and create changing pressure environments for anything orbiting nearby. A hypothetical distant planet would not orbit through empty space, but through a region increasingly filled with matter previously lost by the star. In some epochs that material might be thin and diffuse, in others denser and more structured. Either way, it marks an environment in transition rather than a stable planetary setting. The same mass loss that enriches the future galaxy degrades the immediate environment of the star. This reveals a deeper truth about life and stellar evolution. The most important stars for making heavy elements are not usually the best stars for hosting quiet worlds. Massive stars create carbon, oxygen, silicon, calcium, iron, and many other ingredients later incorporated into planets and living systems. Yet their own neighborhoods are often too intense, too brief, and too unstable to allow those ingredients to organize into long biological histories. Smaller, steadier stars benefit from the prior work of larger stars. In that sense, life around stars like the Sun is indirectly dependent on the violent lives and deaths of stars unlike the Sun. Stevenson 2-18 helps illustrate this asymmetry. It is not a cradle for life. It is a forge whose products will become useful only elsewhere and later. There is also the matter of the final explosion. Any surviving outer planets, if they existed at large distance, would face the eventual supernova, an event capable of stripping atmospheres, driving shock waves through surrounding material, and radically changing the radiation environment on short timescales. The death of the star would not gently conclude a planetary era. It would abruptly terminate it, or leave behind a devastated remnant system orbiting a neutron star or black hole. Whatever small chance of long-term biological continuity might be imagined around a massive star ends at this stage with overwhelming force. The future of Stevenson 2-18 is therefore incompatible not only with mature life, but with stable habitability in any familiar sense. Yet the star remains deeply relevant to the existence of life in the galaxy. The oxygen in water, the calcium in bones, the iron in blood, and many of the heavier elements needed by rocky planets are linked to generations of stellar nucleosynthesis, including contributions from massive stars and their explosive deaths. Stevenson 2-18 represents one of the most extreme visible stages in that larger cycle. Its value lies not in providing shelter, but in manufacturing and dispersing ingredients. Life-friendly systems are more likely to form around longer-lived stars in regions already enriched by earlier stellar generations. In those later, calmer settings, chemistry can proceed slowly enough for planets to cool, oceans to persist, and biology to develop over immense spans of time. Hypergiants contribute to that future precisely because they do not keep their riches to themselves. They release them. This is why the contrast between Stevenson 2-18 and smaller stars is so instructive. The giant star appears magnificent, but it is a place of instability, violence, and accelerated change. The modest, long-lived star may appear less dramatic, yet it is the more plausible partner for habitable worlds. The galaxy needs both roles. It needs extreme massive stars to enrich the medium, and it needs quieter stars to host the worlds built from that enrichment. Stevenson 2-18 therefore belongs on the side of origin rather than refuge. It is one of the makers of the raw material from which future planets and future life may arise, even though its own immediate domain offers almost no lasting welcome to either. The story of Stevenson 2-18 ultimately widens beyond the star itself and becomes a story about the Milky Way as a changing chemical system. A galaxy is not merely a collection of stars shining independently in fixed isolation. It is a long cycle of formation, transformation, dispersal, and renewal, driven in large part by the lives and deaths of stars. Massive stars play a disproportionately large role in that cycle because they burn rapidly, evolve dramatically, and return processed material to space on short cosmic timescales. Stephenson 2-18 stands near the extreme edge of that role. Its size draws attention first, but its deeper significance lies in what such a star does for the galaxy over the course of its life and especially at its end. The giant radius, the unstable atmosphere, the strong winds, and the future supernova are all parts of a single larger process by which matter is altered and redistributed. The star is not only an object of measurement, it is an agent of galactic change. At the beginning of its life, Stephenson 2-18 forms from interstellar gas that already contains material forged by earlier generations of stars. The hydrogen and helium dominating its composition come from the oldest chapters of cosmic history, while heavier elements present in smaller amounts reflect countless prior episodes of stellar evolution and death. In this sense, the star begins as inherited matter, yet once nuclear fusion starts, it becomes an engine of transformation. In its core and later in its shells, lighter elements are converted into heavier ones through successive stages of burning. The exact sequence depends on the star's mass and internal structure, but the broad result is the same. Matter that entered the star in one chemical state leaves it, sooner or later, in another. The star does not create all heavy elements alone, and no single star can explain the full periodic table. But stars like this are among the main sites where the galaxy's chemical diversity is built. The red hypergiant phase makes that contribution visible in two ways. The first is through mass loss before the final explosion. As Stephenson 2-18 sheds gas and dust, it returns matter to surrounding space gradually rather than all at once. That outflow may contain material altered by internal processing and mixing, along with dust grains that condense from expelled matter farther from the star. The surrounding medium is thus enriched not only at the moment of death, but during the star's final life stages. The second contribution comes at core collapse, when the supernova drives much of the remaining outer star into space with enormous energy. The explosion does more than eject material. It accelerates, heats, and stirs the interstellar medium, making the star's death dynamically important as well as chemically important. The surrounding gas is not left unchanged. It is shocked, compressed, and mixed. This process has consequences far beyond the original cluster. The gas and dust released by massive stars do not remain forever near the site of ejection. Over time, they mix into the broader interstellar medium of the Milky Way, contributing to the raw material from which new molecular clouds, new stars, and new planetary systems will form. In this long circulation, the galaxy gradually becomes richer in heavy elements than it was before. Early generations of stars form in a chemically simpler universe. Later generations inherit a more enriched environment. The Milky Way of the present day is therefore different from the Milky Way of the distant past, not only in stellar population and structure, but in chemistry. Stephenson 2-18 represents one small but vivid part of that ongoing enrichment. It stands as a reminder that the galaxy's present complexity has been assembled through many repeated acts of stellar transformation. This is one reason the star matters scientifically, even if its exact radius ranking changes with future measurements. Whether it is first, second, or among several top contenders for largest known star is less important than what it reveals about the upper limits of stellar evolution and the role of massive stars in galactic ecology. Its immense size shows how far a star can expand near the end of life. Its instability shows how weakly held such an extreme atmosphere becomes. Its future supernova shows how that unstable giant will return matter to the galaxy in violent form. The record value attracts curiosity, but the cycle of transformation gives the record meaning. Stevenson. 2-18 is not interesting only because it is large. It is interesting because it shows what large, short-lived stars do to the cosmos around them. There is also an intellectual legacy in the study of such a star. Human beings cannot travel to Stevenson 2-18, cannot touch its atmosphere, and cannot watch its full life unfold directly. Yet from faint infrared light crossing nearly 20,000 years of space, astronomers reconstruct a physical narrative that includes temperature, luminosity, radius, cluster membership, instability, evolutionary state, and probable death. The star demonstrates both the power and the humility of science. Power, because careful observation and theory can reveal the structure of an object hidden behind dust at enormous distance. Humility, because even in this success, uncertainties remain. The exact size is not perfectly fixed. The future remnant is not fully known. The final timing of collapse cannot be predicted. Knowledge here is real, but not absolute. That balance between insight and uncertainty is part of the value of the star as a scientific object. It teaches scale, but also method. In the broadest sense, Stevenson 2-18 links 3 layers of understanding. It is a local phenomenon within a particular cluster, a stellar phenomenon at the limit of late massive evolution, and a galactic phenomenon in the chemical renewal of the Milky Way. These layers fit together. The cluster gives the star context. The star gives stellar theory an extreme test. The star's life and death give the galaxy one more pulse of enriched matter and kinetic energy. Seen this way, the giant does not simply sit at the edge of the Milky Way as a passive wonder. It participates in the long process by which galaxies make later complexity possible. The atoms released by stars of this kind will eventually join colder clouds, then younger stars, then rocky planets, and perhaps in very distant futures, living systems capable of wondering where their materials came from. Stevenson. 2-18 is therefore both an ending and a beginning. It is the late visible expression of one massive star nearing collapse, and it is also one stage in the preparation of future cosmic environments. Its atmosphere is already coming apart. Its core is moving toward failure. Its record-breaking scale is temporary. Yet nothing in that temporary grandeur is wasted. The giant will vanish, but the matter it has altered will not vanish. It will move outward into the wider galaxy, where the work of stellar death becomes the raw condition for new creation. In that exchange between destruction and renewal, Stevenson. 2-18 leaves its deepest legacy. The great red form of Stevenson 2-18 now rests in the mind as something both immense and temporary. It glows in a hidden region of the Milky Way, almost 20,000 light-years away, wrapped in dust, surrounded by cluster companions, and already loosening its hold on its own outer layers. Its size seems to defy ordinary scale, yet that size is only the visible sign of deeper change. Beneath the cool, extended atmosphere, the core continues its silent inward progression toward collapse. Around the star, matter drifts outward in slow loss, carrying the first traces of its future into the surrounding dark. Nothing about it is still. Even in apparent calm, it is a star in transition. In that quiet fact, the star becomes easier to place within the wider galaxy. It is not simply the largest or among the largest. It is one brief and luminous phase in a much older circulation of matter. What it gathers, it will return. What it now holds in its fading envelope will one day move outward into colder clouds and later worlds. The cluster around it will change, disperse, and blend back into the Milky Way. The star itself will disappear, yet the element shaped within it will remain part of later histories that do not yet exist. For now, it remains where it is, remote, reddened, and immense, a fragile giant balanced for a little while longer between brilliance and release,